So this slope is less than 1. B over A is less than 1. So that implies that B better be less than A. And the only way that can happen is if D is less than or equal to 0. So if D were 1 or more, here I'd have A, here I'd have something bigger than or equal to A. When I add them, the leading term can only get bigger, but it has to be smaller. That is, it can stay the same or get bigger. So if D were positive, you'd get a contradiction.
How does the terms with power greater than A get cancelled then? If D is negative, how does the terms of order greater than or equal to A be cancelled?
They don't have to be canceled.
Well, but you said you end up with something less.
Right. So
the
if D is minus 100,
yes,
A is bigger than B.
Yes.
So, something.
Yeah, but that side. But what about the partial U?
That's going to be bigger than or equal to
So
this.
The term there is.
They may be canceled by this product. In fact, they will be. So this is a product of power series.
No, if D is negative, then the D plus A minus 1 would be lower than A.
Yeah.
So how can
it get canceled by the terms of B? This will be the leading term, and it'll have to equal the stuff
then
here.
You still have the partial
and then,
U. And you still have the partial U.
Yeah, and then.
So how can the equation be balanced then?
I'm looking at the lowest order term. I'm not adding anything here.
Yes. So the terms that are higher order than A, on the left side,
right,
can never be cancelled to give you something that has order lower than B.
What?
Has
Let's
order
talk
B.
about it later. I have a power series on one side.
Yes.
And a power series on the other. I equate coefficients.
Yes.
Yeah.
Oh, you equate coefficients.
Yeah, sure. This is an equation of.
Okay. So you set the equation on U on those things to be zero then.
Yeah.
But you can't because you assume that the degree of U is already at least A. The order, rather, you call it.
So if D is negative, these terms will.
Yes. With what?
What am I saying?
Right.
This goes up. So what will happen is that it won't equal A, it will go up.
All right.
B is less than A, right?
Yeah.
So B starts off long before A starts. It starts with minus 300.
Okay. You have what?
So this starts with minus 300. A starts with 100. H has negative terms.
The degree of the power series goes up, right?
Yeah. Not down.
Okay, not down.
Okay.
Yeah. Okay. Yeah. Sorry about that. Yeah.
By the way, I don't want to get too excited because
I was thinking
took me a long time.
No, I'm thinking about polynomial. Sorry about that.
Yeah. Right.
Yeah, sorry. Okay, my mistake.
So I'm not going to do the proof in the other case. What I'm going to do, rather, is when you don't have the low power condition, that means that there has to be some term up here. Maybe there are two terms, but there certainly isn't a term. There could be a term here as well, but there is a term up there on the line. And if you think about it, there'll be another term here. And so somewhere inside this triangle, will be some other term. It could be this one, it could be here, it could be here. But in any case, no matter what happens, there'll be a line whose slope now is bigger than or equal to -1. This was -1, bigger than or equal. So there'll exist a mu bigger than or equal to -1. And for that mu, you can choose a u and a v so that d is bigger than 0. I'm not going to go through the proof. It's the flavor of it is the same as this.
How do you know you can get a point where you have the slope? How do you know you have a point?
So,
Right. Yeah, there's just one
you mean, so, why do I know I
just
have a
one point. You
point?
just have one point.
Well, there can't be just one point, right?
Oh.
So there could be one point here, but this is the stuff of lower or lowest order.
Right.
So there have to be other points, and if they were all above here, then you could divide through by u, and you don't want to do that. We don't have details, but it's okay. Great.
Yeah.
So this is the key observation. This is the meaning of the low power condition for when one thinks of it in terms of the algebraic curve. So if you just think in terms of the algebraic curve, the low power condition gives you power series solutions of a certain kind and forces a derivation to be like this.
Amazingly difficult to get that kind of derivation.
So where are we? So we have now this p of y going from 0. The low power condition implies, well, there are uv, okay, t, the derivation such that du is v, and the order of h, what did I say? Okay. And not the low power condition implies that the order of h is positive. So I've created solutions with this. So, now to talk about functions, I want to restrict myself to this being a sufficiently large algebraic extension of this. Okay, by sufficiently large, in order to do this power series stuff, I need to throw in a finite number of algebraic elements. So the Newton polygon process, when I'm solving for the coefficients, I have to solve polynomial equations, so I may have to expand things a little bit. It turns out I only have to throw in a finite number of things. This Newton polygon, the way it goes through the proof, one generates solutions one step at a time, and at some point, you are just solving linear equations. Okay. So, let me the first proposition. So I'll first say, assume that P does not satisfy the low power condition. is the terms of smallest degree. There's something involved that doesn't just involve y. Then, if I restrict to some open set, there exists some open set O in here, such that for x0 and O, there exists a function, and I'm going to, sorry, don't want to state it 100% precisely, such that 1, f is analytic for small c and analytic in U O cross U, where U is some neighborhood of 0. Okay, it's two variables. 2, f of x0 is identically 0. And 3, for c not equal to 0, f of x c is a non-singular solution of p of y prime equals 0. Yeah, I presume you can read this. So for c not equal to 0, y is this. So fixed c, it's a function of one variable. It's a non-singular solution of this. It's a solution of this that doesn't satisfy the separate. Okay, so if the low power condition does not hold, 0 can be embedded in an analytic family of non-singular solutions.
X0, that's X0.
Yeah, what does this?
Line number 4. It's first character.
X node.
So what I'm saying is the following.
Everything is
Here
exceptional.
is x, y space.
Everything should be
Here's
exceptional.
something. There is some neighborhood
Oh, no.
of this point such that in this neighborhood,
Yeah.
I can define a family of solutions. X0, I'm sorry, there's nothing. It has nothing to do.
Yeah,
Right,
Okay.
right.
forget X.
So there's some open
So,
set
right.
Yeah.
in which I can define
Yeah.
solutions.
Right.
Yeah.
Need X0.
Such that, well,
You can all see this is the first time I've spoken about this.
well, yeah, just pick your X.
So,
Yeah, you just, yeah, I think you have. a-
so in particular, as a corollary, if P does not satisfy
There exists an O and a U.
the low power condition, then this ideal, and again, I'm assuming always that 0 is a solution of P, is not an essential, or is not a singular component. And the reason is this f of xc, is for all c not equal to 0 is going to be a non-singular component. So it'll satisfy that ideal. And by continuity, it'll satisfy it when c is 0. So in particular, so if y equals 0 is a solution of this other ideal, that ideal is a subset of this.
Yeah.
To say that the solution of this is a solution of this is the same as saying that this is a subset of that. So this ideal contains this, so it's not part of the irredundant decomposition. So this is half of the low power theorem, the analytic proof. And let me say how one proves this, and then I'll stop proving things and just state some things. The proof is what I just erased. I'm working in here. I have UV in here. P of UV equals 0. I have a derivation. D was d dx. H, this is h of t. Du dt is v. And the order is bigger than or equal to 1. It's bigger than 0. So the idea now is I want to think of u and v as functions of x. I mean, here they're functions of t, and I want to think of them as functions of x. Well, the way to do that is to consider this differential equation, dh dt dx is h of t in x. This is a power series in t, its coefficients are functions in x. If I'm sufficiently careful, and believe me or not believe me, if I am, I can think of h as analytic in t and x in some small neighborhood, for some values of t and x. If I restrict domains enough, I can do that. So I have an analytic solution. So there exists some t of xc satisfying dt dx is h of tx, and the initial condition is this. So I've put in the initial condition, and from theorems on differential equations, we can get it to, t and c. So t depends analytically on the initial conditions. In classes on differential equations, you get existence theorems, something like this, and if it's a good class, they also describe how the function depends on initial conditions, but it's true. Okay. So now I just look at u of t of xc. And the derivative with respect to x of this new function is precisely v. df dx is v. See? And that's it. That's my solution. And this then satisfies the original equation. So it's this again is, this part isn't in Cohn's paper, but this business of looking at this, first solving things as functions of t, and then if you want to make sense of it, find an h, and I think this is implicit in Hamburger's paper. Again, it's either my German or my mathematics is strong enough to really get it from there, but it's there somewhere.
So where is the extension business?
So I needed to, so this h, I'm working here.
Right.
To really get u and v, I couldn't start with, I needed to assume this was algebraically closed. In fact, you don't need algebraically
I see, you just need whatever you need.
You need whatever you need, and in fact, it's a finite amount of stuff.
Right.
So if I have a finite number of algebraic functions, surely I can find a domain within that. Okay, so let me finish by stating the other half. So the proposition 2 is, I assume he satisfies the low power condition, then for any L bigger than or equal to 0, I want to let I sub L be this differential ideal intersected with the polynomial ring of this. So I'm looking at those differential polynomials in here that only involve up to order n-1. And of course, this should be an L. And maybe in fact, I think we can show that this is so there are two results. If this is the L-fold copies of zeros, is a 0 of L, then there exists a solution and there exists, now I need an open set such that for x0 in O, I can get a solution there exists a non-singular solution y of x analytic near x0, not necessarily at x0, but in some neighborhood where x0 is on the boundary, continuous at x0, such that limit So not only does the function approach 0, but all of its derivatives up to order L. So the picture looks like this. Becomes very flat here. So I'm saying in some neighborhood, I can always get this 0 solution as a envelope. In fact, it's a very high order envelope. And part 2 is that if if y prime has degree n in P, then this is not a 0 of y sub n. So in particular, 0, the identically 0 solution can't be a 0 of this, because if it were, 0 up to the so-and-so unit derivatives would be the 0 here. So the 0 solution is not part of the general solution, and so that component is an essential component. So this is the other half of corollary. Not LPC implies is a singular component. Sorry, LPC implies this. And this, in turn, since I've run out of time, maybe people want to talk about it later, this is enough to show that you only have to go this far to get generators. That from this, I can deduce that this is enough. It's a little technical. I don't have time, but I don't want to do that. Let me just say that Richard Cohn, the last few papers of his that I've seen were devoted to this question of when does y equal 0? When is it a 0 of the general component? Independent of whether or not it's an essential component. This is what's called the RIT problem. When is the y identically 0 a solution of this? And what he did was he restated a lot of what RIT had done in terms of valuation theory, using Sally Morrison's work. So RIT had looked at second order equations and was able to effectively answer that question. The low power theorem does it for first order. For second order, you need more. And Cohn was, it seems to me, in the process of unwinding RIT's proof. He had taken an essential part of RIT's criteria and stated it in terms of valuation theory. And it's a shame. Nobody's working on it anymore. Valuation theory has progressed quite a bit. Certainly, people working on desingularizing varieties know a lot more about valuations now than we did before. It would be nice if somebody would go back and look at that. Somebody who knows something about valuation theory, just not me. Nonetheless, this unifying, this singular solutions being envelopes or members of families, the low power theorem, and this business about generating ideals really can all be put in, let's say, a modern context using this very nice idea of Richard Cohn, where you just look at Puiseux, the Newton polygons and power series solutions. So So I've run out of time and probably patience. So thanks very much.
Any questions?
Sorry. You say here is for all L greater than or equal to 0.
Yeah.
So you're saying that in order to find the generators, you only need up to L equal to capital N? Is that right?
Yeah.
Okay.
It may be L minus 1.
Yeah, I know. Okay, yeah, it doesn't matter, right?
Yeah. Nice.
Yeah. So,
Yeah, that is
you know,
nice.
boy,
It's L.
it's L. It's L. It really, it's very much a first order phenomenon.
Did you-
Presumably you've thought about this issue. So,
Have you looked at Ritt's second order paper, that long?
yeah.
Yeah,
Actually,
and-
Cohn, in his paper on valuation theory and singular solutions, outlines what Ritt did.
Oh,
He gives us a summary, a one-page summary, which anybody who's interested in this paper must read Cohn's description
yeah,
first.
yeah.
He's really done people
very
a
clear.
big favor. So, you know, Ritt, this power series business is embedded in Ritt.
Yeah.
I'm going to just quickly say that
Yeah.
Ritt
Say
was
more about
very interested in writing the derivative as a power series in the solutions. These are called Y solutions.
Oh, God.
And
That's how we did.
this kind of formula appears whenever you see anything about the low power theorem or anything that Ritt has done in this subject. And what Cohn did was interpret the existence of such a formula in terms of operations.
I'm sorry, I couldn't hear the last thing you said in terms of
Valuations.
Valuations.
Well, thanks.
More questions? Thank the speaker again.